Swayam Prabha. Digital India. Educated India.
In this week and in the next week, we will deal with composites. We will see the behavior of composite plies and composite laminates, and we will see how a composite laminate which has piezoelectric patches can be analyzed. Now, before going to that, let us have a brief introduction to composites. This introductory lecture will contain these topics. At first, we will see what a composite is, and then we will see important features of composite materials. After that, we will see the present scenario of the overall composite market. Then we will talk about applications of composite materials in different fields, and then we will see various types of composites. After that, we will see properties of various various constituents, and then we will talk about honeycomb composites. So, a composite is a combination of two or more different materials which are chemically distinct and they do not react. And the kind of composites that we will talk about in this course are composites at macro scale. So, they are mixed at macro scale. So, the constituents can be identified by the naked eyes if we look at the composite, and constituents have distinct interfaces. An example can be a plywood. Now, the type of composite that we talk about in this course is called fiber reinforced composite. In short, we call it FRP. Now, there is something called alloys also, but these alloys are micro scale composites. So, that is the main difference between alloys and the kind of composites that we deal with. So, in alloys the component cannot be identified if we see them. An example is a steel. So, we will restrict ourselves to fiber reinforced composites. So, here are some important properties of composites. These composites have high strength, they have high stiffness. So, if we take a traditional material like a metal, and if we take a composite of the same weight, then we generally get high strength and stiffness in the composite. So, the strength to mass ratio or the weight ratio, stiffness to mass ratio or weight ratio is generally higher for composite, and they have good corrosion resistance properties, they have good wear resistance, and they are lightweight, and they have high fatigue life, because these composites generally look like this. We have matrix and fiber laid up. So, if there is a fatigue crack, generally its propagation is arrested by this kind of layup, and they have noticeable temperature dependent behavior. They have high thermal insulation, high impact resistance, high acoustic insulation. So, in applications like stealth, because it has good acoustic insulation properties, composites are widely used, and these materials give unique design flexibility. That is a very important point. So, if we change the fiber orientations, or if we change the orientation sequence in a laminate, you can change the properties a lot. So, we can get different types of properties, different types of unique features by aligning these fibers. So, that is a unique design flexibility which we get from composites, and there is ease of fabrication. So, if you want to get any shape, we can prepare the mold accordingly, and accordingly we can lay up the composite and make the composite. These properties depends on the constitutive materials and their distribution, their interaction. And for our case, the constitutive materials are reinforcement elements like fiber and matrix elements, which is polymer for our case. If we try to trace the origin of composite, we can go back to ancient times. In the ancient times, people of Israel used straw to strengthen mud bricks. Plywood was used by ancient Egyptians. So, these are all composites at the basic level, and then we have made lot of advancements. Even in the medieval times, swords and armors were constructed with different layers of metals. Now, here is a brief outlook to the global or Indian market of composites and how it is expanding. In US, FRP composite industry is growing at an average of 6.5% since 1960. If we talk globally, the market size was 105.75 billion US dollar in 2022, and it is expected to reach 191.36 billion US dollar by 2032. In India, the Indian composite industry has witnessed single digit growth in recent years and is expected to grow at a compound annual growth rate of 8.2% in the next 5 years. The per capita consumption of composites in India is around 0.3 kg against 2.5 kg in China and 11 kg in US. So, there is a scope of tremendous development in this field in near future, and we can see that by this number. If we look at the distribution in different sectors as per 2016, then logistics sector used around 25.1%, construction and building has around 13.8% share, electrical and electronics has around 14.4% share, defense and aviation around 13.4%, pipe, tank, things like that around 10.4%, wind energy at around 8%, consumer goods around 7.6%, marine field around 2.7%, and other sectors around 5.1%. So, these all statistics are taken from various resources. So, they are referred here. You can go and look into it in more details. Now, let us talk about applications in various fields. Space industry uses composites a lot due to high strength to weight ratio and high thermal stability. We can see a solar panel here, and these panels, in these panels composite finds a lot of application. Here we can see Hubble Space Telescope. Graphite epoxy truss is used to stabilize and support the structure. Similar thing can be seen in mirror backplane of JWS telescope. In aviation industry, composite structures find a lot of applications. So, again the advantageous features that generally makes this material useful for this field are high strength to weight ratio, excellent fatigue resistance, which is very important, and high thermal stability. So, if we look at a aircraft, for example, it is a Boeing 787 Dreamliner aircraft, we can see that there is around 50% of the entire constituents is composites, advanced composites, and there is 20% aluminum, 15% titanium, 10% steel, and others around 5%. So, various aircraft parts like wings, fuselage components, interior parts use composites. In automotive industry, its use is rapidly growing. We get reduced body weight through composites because it has high strength or stiffness to weight ratio, and accordingly we get enhanced fuel efficiency also. And also, if we talk about high speed cars, its impact resistance is also very useful. So, various automobile parts like body panels, chassis components, interior parts have composites. So, these articles shows a good overview of the use of composite in this industry. If we go to the renewable energy sector, wind turbine blades are made of composite because it can withstand high loads and provide optical performance accordingly. And in wind, so the modern day wind turbines are becoming larger and larger, even there are wind turbines of radius around 90 meter or so. So, a material which does not increase the weight too much and give good performance is very important, and in wind turbine its pitch control is very important for getting better performance and also reduce the aeroelastic instabilities. So, composite materials are quite helpful for those cases. In solar panel also composite is used due to its lightweight and resistance to weathering. We can see the various applications here in the sports industry. Examples can include tennis racket, golf, the equipments in golf, bicycles, helmets and so on. So, composite materials provide low weight, strength and stiffness, impact resistance, and that is why these are used a lot. In construction industry, composite is finding rapidly growing application due to its high strength, corrosion resistance and reduced maintenance cost. Now, applications can include bridge decks, building panels and so on, pipe, masts, crash barrier, railway track, beds etc. have use of composites as well. Now, let us talk about marine industry. So, we said that we saw that composites have good corrosion resistance. So, that is quite important for marine field. So, that is why composite is used, and apart from that its lightweight make it fuel efficient. So, there are various applications in petrol boats. Composites are used. The first composite petrol boat was built in 1960s for US Navy, and then mine countermeasure vessels are used for locating and destroying sea mines. Now, in this kind of applications we need non-magnetic materials so that they cannot be detected. So, previously it used to be made by woods, but because we do not want to destroy nature, we do not want to use too much of wood. So, composite comes into picture here, and there are several mine countermeasure vessels which have been constructed by composites and are being constructed. Covers, hydrofoil and supercrafts, composite superstructures. So, the superstructure of a ship are generally made of composites. So, again there are growing applications of composite there, and propellers, rudders, bulkheads, doors, machinery and engine components, various parts of submarine structures also have composites. If we look at the day to day equipments, electronic equipments, composite is also being useful there. So, smartphones, laptops are examples. The properties that are useful here are electromagnetic shielding, thermal resistance, structural stability and of course, its lightweight. In the medical field, composites are used for prosthetics, orthopedic uses are there. In dental also, dental materials are composites. So, here it is used because of its biocompatibility, strength and flexibility. We can see a prosthetic leg here. Now, we will see various types of fiber reinforced composites. So, there is something called particulate composites. So, in particulate composites, particles of various shapes and sizes are dispersed in a matrix. So, if we see a composite like this, so in the matrix there are particles of various shape and size, and because they are randomly placed and oriented, so it is can be treated as quasi homogeneous and quasi isotropic. Now, these particles can be spherical, cubic, tetragonal or different kind of shape. Now comes fiber reinforced composites. So, as the name suggests, we have fibers that are placed in matrix. Here the fiber length is much greater than the cross sectional dimension. So, they are long fibers. Now, orientation of the fibers here highly influence the stiffness and strength of the whole system, and matrix are polymer matrix, they hold the fibers. Now, this fiber reinforced composites can be single layered or multi layered. So, there can be just one layer with some fiber orientation, or there can be many of those which are stacked one over another. So, something like this, where there are many layers which are one over another. Now, each layer is called a lamina or ply. Now, these multiple layers can have different ply orientation and they can have different constituents also. Single layered composites can have continuous fiber reinforced composites, or they can have discontinuous fiber reinforcement also. So, when it is discontinuous, so there are fibers of different small lengths. Now, this fiber length affects the property of the composites. In multiple layered, so there can be hybrid laminate. So, in hybrid laminate, the property of the constituents can be different as we go layer by layer, and at the same time the orientation of the fiber can also be different. Whereas, if it is not hybrid, just the material properties are same, the constituent properties are same layer by layer, but the orientation can be different. Continuous fiber reinforced composites can be unidirectional. So, if we lay the composites just in one direction, so if our one ply look like this, so it is called a unidirectional composite, and there can be bidirectional where there are plies which intersect each other and they are laid in different directions. Again, in bidirection there are woven or braided, we will talk about it. When it comes to discontinuous fiber reinforced composite, there can be random orientation or there can be preferred orientation also. Random means the various short fibers are randomly oriented, and if we want to have some preference in the direction, then generally what is done is these chopped fibers are tightly bonded first and then sprayed with liquid resin against a mold. Now, in bidirectional composite there can be braided composites. So, braided composites are fibrous composites that consist of long fibers impregnated by a matrix. Braided composites are characterized by the organization of their yarns in such a way that they are interlaced diagonally about an axis. This characteristics is often termed an angle ply composite. As with other composites, braids are impregnated with a matrix to form a composite to improve their properties. Strands in braids undulate above and under each other, and these strands are said to be crimped. Because of their interlaced structure, braids are tougher than traditional laminates. However, because of the crimp angle of the strands, they are also less stiff than traditional laminates. So, a more description about the braided composites can be found in this handbook and in various papers also. Now, here we talked about one term which is yarn. A fiber yarn is a discontinuous strand or thread like structure composed of fibers twisted or spun together. Now, it is a fundamental unit which is used in textile manufacturing to create fabrics and textile. Now, there can be different types of braids. Here we can see some 2D braids. It is a diamond braid, it is a regular braid, and it is a Hercules braid. Similarly, there can be woven composite. So, in woven composite, yarns are interlaced in a specific pattern to form a textile like sheet. Now, interlacing pattern of fibers in a woven composite is achieved through a weaving process similar to that used in textile manufacturing. Again, there can be 2D or 3D weaving. Now, here we can see a cross sectional view of a woven composite. Now, in this course we will stick ourselves to unidirectional composites. So, we will consider composite where there can be many plies, but each ply has just one direction of composite orientation. Now, let us look into the fiber different constituent properties. The fiber that we generally used in fiber reinforced composites are glass fiber, aramid fiber, carbon fiber and boron fiber. Again, in glass fiber there can be E-glass fiber and S-glass fiber. E-glass fiber costs less, and these are the different properties. So, these are the typical diameters of a fiber. Here specific gravity is given. Tensile modulus in GPa is around 70 to 80 GPa. Tensile strength is around 3 to 4 GPa. Ultimate elongation in strain is around 4 to 5%, and coefficient of thermal expansion varies from 5 to 2 into 10 to the power minus 6 by per degree centigrade. Kevlar fiber properties, again the typical diameter is somewhat same, specific gravity is little less, tensile modulus is higher than the glass fiber, tensile strength is somewhat same, ultimate elongation is less than the glass fibers. And if we talk about carbon fiber is much costlier than glass fiber, however, they are much better properties. So, in aerospace applications carbon fibers are very widely used even in Formula car also. So, depending on the applications fibers are chosen depending on how much strength we need, how much accuracy we need and what is our budget. So, accordingly fiber has to be chosen. If we talk about carbon fiber, the diameter is less than the glass or Kevlar fiber. Its specific gravity is comparable with the aramid, and carbon fibers tensile modulus is much higher than the glass fiber. And then we have the tensile strength which is comparable, ultimate elongation is much less, and boron fiber have these properties. Its specific gravity is much less, its tensile modulus is much higher, tensile strength is somewhat comparable. Now comes polymers. So, when we talk about these polymers, I mean polymers means the matrix material. So, the matrix is generally a polymer which we call resin, and this resin is mixed with a hardener and then it is cured and it forms a matrix. Now, these polymers resins can be thermosetting or thermoplastic. Now, thermosetting polymers, once it is cured and it is hardened, if we heat it we cannot melt it. Now, thermosetting polymers example include polyester, vinyl ester, epoxy, phenolic. Their specific gravities are more or less same. If we talk about tensile modulus, we get more tensile modulus through vinyl ester. Poisson's ratio is again somewhat comparable. Tensile strength, again we can see for polyester for 40 to 90 megapascal, vinyl ester 65 to 90 megapascal, and epoxy 35 to 130 megapascal, phenolic around 50 to 75 megapascal. Compressive strength in megapascal it is 90 to 250 for polyester, 127 for vinyl ester, 100 to 200 for epoxy, 200 for phenolic. Elongation 2.5% maximum elongation, vinyl ester 1 to 5%, epoxy around 1 to 8.5%, phenolic 2%. Coefficient of thermal expansion 60 to 200 into 10 to the power minus 6 per degree centigrade. For vinyl ester and epoxy around 53 or 40 to 70 in the same unit. If you look at the water absorption properties, polyester absorbs water 0.1 to 0.3%, epoxy 0.1 to 0.4%. Then comes the matrix which is thermoplastic. So, here after curing we can heat it and melt it. Now, there are different types of these polymers. ABS used in small craft, for example surfboard, but they have a poor weathering. Specific gravity 1 to 1.05, Young modulus 3 gigapascal. Tensile strength, tensile yield stress is 35 megapascal, tensile failure strength 50%, heat distortion temperature in centigrade is 100. Similarly, there are various types of these polymer resins and we can see their comparisons. Now, let us spend some time in talking about the honeycomb composites. In honeycomb composite is there are two face sheets. The face sheets can be a fiber reinforced composite laminate and at the core there is some core material. So, we can see a FRP at the face. So, they are called face sheet. Now, again face sheet always does not need to be FRP, it can be metal also, and the core can be honeycomb comb, maybe of aluminum. There can be foam, there can be cellular core, and so on. Now, we get tremendous advantage by using honeycombs. We get much more strength and stiffness with less weight. So, here we can see that these fiber reinforced plastics, they have high Young modulus. So, that and they are placed at the two extremes. So, that takes care of the bending, and this deep core takes care of the shear. So, accordingly we can go for better lightweight and high strength design with honeycomb composites. Now, for example, here we are showing one airfoil section of a wind turbine blade. So, we can see that at different places there are foam cores and various laminates are used, and at the surface there is a gel coat for better finish and better protection. So, again these laminates have different names like SNL, Triax, Sartex. So, mostly unidirectional laminates are there. So, this gives an overview of how these composites are placed and the foams are placed and the protective materials are placed to make a real life airfoil composite structure. So, with this brief introduction, I would end this lecture here. Now, we will gradually move on to analysis. So, as we said, in this course we will restrict ourselves to unidirectional composite. So, in the next lecture we will start looking into the properties of a unidirectional ply. So, we have the properties of each individual constituents here. So, for example, in a glass fiber reinforced composite we can have the properties of glass fiber and the matrix material. The matrix material can be epoxy or polyester and so on. Similarly, in a carbon fiber composites we can have the properties of carbon fiber and the matrix material, and from those constituents we will see the properties of a lamina or ply. So, we will do some kind of homogenization, so that instead of having to deal with the individual properties, we will deal with the equivalent property of a composite, and that we will start defining from the next lecture, and then we will gradually move on to the properties of a laminate and its analysis. So, with this let us end the lecture here. Thank you.